Why RC models are important to us in the test pilot business is the first time you climb aboard one of those airplanes to go do something that may have never been done before, it's actually been simulated and been flown a lot and scaled down and tried on many different platforms.
Rarely do test pilots just go out and hop in an airplane and give it a whirl and see what happens.
Sometimes it's just too unsafe to go fly that aircraft in that flight regime. When we first start out, maybe we test a concept on a smaller scale.
If you want to try a new shape of a wing, or you wanted to try a new whole airplane concept, it's much cheaper and easier. You can do it for orders of magnitude less.
Model testing is a stepping stone towards a full-size aircraft.
Hi, I'm Red Jensen, Chief Pilot for Subscale Research Aircraft here at Armstrong Flight Research Center. Welcome to my lab. Here at Armstrong, we use a variety of subscale aircraft to test out new and emerging technologies that may or may not make it to the full-scale world. And we've been doing this for a very long time. As you can see, these are not your normal model airplanes. This is our Droid aircraft, and this is really a flying test bed in the backbone of the model lab. We can use this to test out many different technologies. For instance, we currently have ADS-B on board, and we also use this as a tow plane for our towed glider project. This is our twin glider air launch concept. The idea here is to tow a rocket up underneath with a payload on it and launch it from about 40,000 feet. This will reduce our launch costs to orbit. This is Photo 1, which is an octocopter, and we use this for a variety of filming applications around the center. This is Hue, which is basically an RC airplane, except that we're testing an experimental flight computer, which allows researchers and students alike the ability to customize flight control systems. This is Prandtl, and this is research into lowering induced drag, or a new way of thinking about wing design. Here in the model lab, one of the cool things about us is we're a one-stop shop. Here is where we configure and maintain our autopilot and data acquisition systems. Over here, we have a 3D printer. Almost everything we build here is a one-off, so this allows us the ability to build parts instantly right here in the lab. And when it's time to fly, we have a completely self-contained mobile ground control station that allows us to operate at any austere environment.
We're going to do the control check.
Left roll, right roll. Right rudder. Yep.
We're ready to hook up the fibers.
I'd like to go back to the control algorithm one more time. I want to get it to its neutral position.
Go left, go right, go right.
We're good. Okay, from a pre-flight standpoint, are you guys ready to go?
We're ready. We're ready.
We're at 100.
Good to go.
Take off 720.
Thank you. Edwards Tower, NASA UAS is airborne U.S. work area surface to 3,000 feet.
All right, Red, move the radius, 500-foot radius, and then move it closer to you. Perfect. Holding 55 knots, capturing, climbing to 3,000.
Hand off to pilot.
I got it.
In a lot of people's eyes, it's not as glamorous. It's not an F-18 or an F-15 or something like that. It's a small airplane. But what a lot of people don't realize is you can get an amazing amount of data and testing done very quickly with a model aircraft rather than waiting years to see if your full-scale article is going to fly.
Stand by for auto. 3, 2, 1, auto.
The autopilot is capable of getting the standard accels, airspeed, altitude, position through GPS, things like that. Some of the aircraft have an additional data system on board. For instance, the APV-3 FOSS aircraft has a fiber optic strain sensing network in the wing where we're measuring bending deflection to do real-time gust load alleviation. How much does the wing bend, and how much do we have to deflect a control surface to neutralize or minimize that bending moment? Hue has an open architecture type autopilot, which means it's not locked to a certain configuration. The beauty of that is you can make Hue behave like another airplane simply by changing the control laws. If you wanted to make it fly like a Cessna 310 or a T-38 or something like that, you can emulate these different types of aircrafts. And the advantage of that is, again, low cost, rapid development, and much quicker to fruition. I like to say that we do the stuff that's either too dangerous, too boring, or not enough money for. For instance, the T-Gals. It's kind of a wild concept. You would never build a manned airplane right off the bat. So we build a subscale model, prove the concept, and then go forward with that technology. Another thing is the auto ground collision avoidance system, where you're flying an aircraft at a blind canyon and let a computer take over and avoid the obstacle. Well, that's obviously very risky to do in a manned aircraft, so it makes perfect sense to do it in a subscale aircraft where if something happens, well, there's no harm to any person. I feel that Armstrong uses SUAS to enhance the center's capability. Somebody can have some wild harebrained idea. They can come to the model lab. We can either fit the technology in an existing platform, or we can build an all-new platform to test this thing. Sky's the limit.